Module 1, Lecture C, Control Flow Basics. By the end of this lecture, you will be able to write conditional statements that classify medical values using clinically defined thresholds, use loops to process repeated measurements such as daily temperatures or glucose readings, and combine comparisons, logical operators, and simple output to create readable clinical summaries. Clinical conditionals. Threshold classification. Threshold classification means interpreting a measurement by comparing it with clinically defined limits. In healthcare, values such as blood pressure, glucose, or temperature become meaningful when they are labeled as normal, elevated, or concerning. In programming, conditional statements support this same process by checking a value against a standard and assigning a category, helping make healthcare decisions more consistent. Threshold classification depends on clear boundaries and a well-ordered sequence of decisions. In clinical measurements such as glucose, pulse, or cholesterol, the program must define whether boundary values belong below, within, or above a range. Careful threshold logic prevents misclassification and makes clinical summaries safer, clearer, and more accurate in how they communicate urgency. Threshold classification shows how programming can apply clear decision rules to clinical data, but it cannot replace clinical judgment. Values such as temperature or oxygen level must be interpreted in context, because their meaning can differ across patients. Programming helps organize information, support communication, and recognize patterns, while professionals remain responsible for judging what the data means. Python code. Threshold classification. Clinical thresholds help convert numeric measurements into clear categories. When using conditional branches for vital signs, the boundary values must be checked carefully to ensure each measurement is classified correctly. A small set of patient measurements is recorded for later health classification. These include a body temperature of 38.2 degrees Celsius, oxygen saturation of 93%, and systolic blood pressure of 146. Temperature is classified by comparing it with clinical thresholds. A temperature of at least 38 degrees Celsius is labeled as fever, while a temperature of at least 37.5 but below 38 is labeled as elevated. Anything below these thresholds is considered in the expected range. Oxygen saturation is classified using simple thresholds to quickly assess a patient's status. A level below 90 is considered an urgent low range, while a level from 90 to below 95 is below the expected range. The saturation of 95 or higher is considered within the expected range. Systolic blood pressure is classified using simple thresholds. A reading of 140 or higher is considered high range, indicating hypertension. A reading of at least 120 but below 140 is elevated range, suggesting prehypertension. Lower readings are in the expected range and generally indicate normal blood pressure. The output begins with a brief summary header, then reports each vital sign with its clinical classification. It shows the patient's temperature in Celsius, oxygen saturation percentage, and systolic blood pressure in millimeters of mercury, each paired with a label based on predefined thresholds. Together, these results give a concise overview of the patient's vital sign status. This Python script uses conditional statements to classify patient measurements against clinical thresholds. In the example output, a temperature of 38.2 degrees Celsius is identified as fever. Oxygen saturation of 93% is below the expected range, and systolic blood pressure of 146 millimeters of mercury is in the high range. Threshold-based classification. Threshold-based classification helps turn clinical measurements into meaningful categories by comparing them with established cutoffs. For example, temperature or blood pressure values can be labeled as normal, elevated, or concerning based on predefined thresholds. In Python, conditional statements apply these rules consistently by checking whether a value is below, at, or above a cutoff, without making independent medical judgments. In threshold-based classification, conditions must be ordered carefully so each measurement falls into the correct category. For values like glucose levels, ranges for low, normal, elevated, and high must be distinct, especially at the boundaries. A clear order, such as checking the most critical category first or moving from low to high, helps prevent broader rules from misclassifying specific cases. Threshold-based classification turns clinical measurements into clear labels, such as normal or concerning, by comparing values with established cutoffs. It can summarize temperature, oxygen levels, heart rate, and similar data in a consistent way that supports communication and decision-making. However, these labels are only a guide and do not replace professional clinical judgment. Python code. Threshold-based classification. Classify clinical measurements using predefined thresholds, so results are labeled consistently. This approach supports educational decision-making by applying simple, standardized cutoffs. The script begins by creating a list of sample Celsius temperature readings. This list stores the data that will later be classified, with each value handled one at a time. The temperature classification function takes a Celsius temperature and first checks whether it is at least 38 degrees. If so, it labels the result as fever range, so the most clinically important condition is identified right away. The code checks whether the Celsius temperature is at least 37.2, which signals a mildly elevated temperature. If so, the function labels it as an elevated range, meaning it is above normal but not yet a fever. This part handles the default temperature classification. If the temperature is not in the fever or elevated range, the function labels it as within the expected range. This gives every input a valid result and keeps the classification reliable. A small set of fasting glucose readings is stored for later classification. The sample values are 68, 91, 112, and 131 milligrams per deciliter, and they can be checked against predefined thresholds to determine each glucose range. A glucose classification function checks a reading in milligrams per deciliter and labels it as low glucose if it is below 70. This flags values under the typical lower threshold as potentially concerning. The code checks whether the glucose value is 99 or lower. If so, it labels the result as within the typical fasting range, marking it as normal and separating it from higher glucose categories. This code checks whether a glucose reading is at or below 125. If so, it labels the result as in the elevated fasting range, meaning the value is above normal fasting levels but not yet in the high-risk category. The final condition classifies any glucose reading above the earlier ranges as markedly high. It serves as a catch-all so that values beyond the elevated fasting range are still given a clear category. The code begins by printing a short header that introduces threshold-based classification examples. It tells the user that the upcoming output will show how temperature and glucose readings are categorized using predefined threshold values. The program goes through each Celsius temperature, uses a classification function to assign it to a range, and then prints a clear message showing the temperature and its category. This gives a concise summary of how each reading is classified. The program goes through each glucose reading, uses a classification function to assign the correct category based on set thresholds, and then prints a clear message showing the reading and its category. This script shows how simple threshold rules can classify clinical readings. It checks temperature values and labels them as expected, elevated, or in the fever range. Then it checks glucose values and labels them as low, typical fasting, elevated fasting, or markedly high. When run, it prints the results, illustrating a basic form of decision support using predefined cutoffs. Threshold-based classification. Threshold-based classification turns clinical measurements into categories by comparing them with preset cutoffs, such as deciding whether temperature or blood pressure is within a normal or concerning range. In programming, conditional statements apply these rules by checking whether a value is below, equal to, or above a threshold. The computer is not making its own clinical judgment. It is simply following rules defined by human interpretation. Threshold-based clinical classifications must use clear, precise boundary logic. Each category should handle values below, at, and above its cutoffs without gaps or overlap. Small wording differences, such as greater than versus greater than or equal to, can change classifications and affect follow-up or alerts. Careful logic supports consistent, reviewable, and accurate clinical interpretation. Threshold-based classification depends on context. Because the same measurement can have different meanings for different patients or conditions, factors like activity level, chronic illness, and age-specific pediatric ranges can change how values are interpreted. In programming exercises, conditional should express precise clinical rules to classify results as low, normal, or critical, while still recognizing that professional judgment is essential. Python code, threshold-based classification. Practice applying clinical threshold rules by comparing values to their cutoff points and reporting the results in clear, concise summaries. A list of measurements stores each patient's name with their temperature in Fahrenheit. This structure makes the data easy to access and supports later analysis or classification using set thresholds. 2 clinical temperature thresholds are defined for classifying patient readings. An elevated temperature begins at 99.5 degrees Fahrenheit, indicating above normal temperature without fever. A fever begins at 100.4 degrees Fahrenheit, marking the fever range. We review each patient's temperature and compare it with the fever threshold. If the temperature meets or exceeds that threshold, the patient is marked as being in the fever range. This helps quickly identify patients who may need prompt attention. This code checks whether a patient's temperature meets or exceeds the elevated threshold. If it does, the temperature is classified as elevated, helping flag patients whose temperature is above normal, even if it does not qualify as a fever. If no early condition applies, the patient's temperature is classified as within the expected range. This default means the temperature is normal because it falls below the threshold for elevation or fever. The code prints a brief clinical summary for each patient, including the patient's name, temperature in Fahrenheit, and temperature category. This gives a quick view of the patient's condition using predefined thresholds. This section checks the boundary case for temperature classification. It tests a temperature set exactly at the fever threshold to confirm that the logic handles this edge case correctly. The code checks whether the boundary temperature meets or exceeds the fever threshold. If it does, it is classified as fever range. Otherwise, it is below the threshold. This makes the threshold rule clear, especially for values exactly at the boundary. The code prints a concise boundary temperature summary. It shows the boundary value in degrees Fahrenheit and adds the classification result, indicating whether it falls in the fever range or stays below the fever threshold. This script reviews patient temperatures and classifies each one as expected, elevated, or in the fever range. It uses clinical cutoffs of 99.5 and 100.4 degrees Fahrenheit, then prints a short summary for each patient. It also checks the exact fever threshold to confirm that this boundary value is treated as fever range. Repeated readings. For loops. A for loop helps process repeated clinical measurements, such as daily temperatures or glucose readings, in a consistent way. It lets a program examine each value in a sequence automatically, making the code shorter, clearer, and less error-prone. This is especially important when working with large healthcare datasets over time. A for loop processes one item from a collection at a time, applies the same check, gives feedback, and then moves on. For example, it can review temperature or glucose readings and classify each as low, normal, or high. This consistent structure supports clear summaries and reliable logic, similar to routine clinical checks. For loops help turn repeated health measurements into useful summaries by applying the same check to each reading. They can count fevers, compare glucose or blood pressure values to target ranges, flag high case counts, or track changes in pain scores. By repeating actions in a clear and systematic way, for loops make patterns easier to identify and communicate. Python code. For loops. Use for loops to practice checking clinical readings in a consistent way. Keep the output brief, clear, and easy to read. We define a list of daily temperature readings in Celsius to represent clinical measurements. This simple structure lets us review the values later to identify possible fever conditions. Begin by setting the fever count to 0, so it can accurately track how many temperature readings suggest a possible fever. The program loops through the daily temperatures using the enumerate function, which provides both each temperature and its position in the list. The position is adjusted to start at day 1, making the output match how days are normally counted. This lets each temperature reading be processed with its corresponding day number. The code treats any temperature of 38 degrees Celsius or higher as a possible fever. When this happens, it updates the status and increases the fever count to track how many readings suggest a fever. When a temperature reading is below the fever threshold, the code labels it as below the fever threshold. This means the reading is treated as normal or not concerning, and the label helps describe each day's result in the output. This line prints a short daily temperature summary to the console. It shows the day number, the Celsius reading, and whether the result suggests a possible fever or is below the fever threshold. The code summarizes the temperature data by counting how many daily readings are in the list. This gives the total number of measurements used in the analysis. The code prints a brief summary of the temperature readings. It shows how many readings suggested a possible fever out of the total reviewed, giving a quick view of how often the fever threshold was exceeded. The script reviews daily temperature readings in Celsius and checks each one against a fever threshold of 38 degrees. It marks any reading at or above that level as a possible fever and counts how many times this occurs. After all readings are checked, it reports the total number of possible fever readings, giving a brief summary of the temperature pattern. Reading loops. Reading loops help programs process repeated clinical measurements, such as daily temperatures or glucose checks, one at a time. They apply the same clinical rules to each value, making it easier to identify abnormal readings. This keeps data review efficient, consistent, and systematic. Reading loops are useful for processing measurements one at a time, such as health readings. For each value, compare it with a threshold, assign a category, and produce a short explanation. This keeps the program clear, accurate, and easy to read, whether the results support dashboards or alerts. Reading loops turn repeated measurements into concise clinical summaries. They can show how often values cross a threshold, whether urgent attention is needed, and what patterns appear over time, such as persistent fever or glucose trends. This makes raw readings easier to interpret and supports faster, more informed decisions. Python code reading loops. Practice using a loop to process repeated clinical readings. Apply the same threshold check to each value. Then summarize how many readings need attention. The code begins by storing daily fasting glucose readings as a list of numbers measured in milligrams per deciliter. Each value represents one day and can be checked consistently to see whether it is within the target range, too high, or too low. Begin by creating 3 counters, all starting at 0, to track glucose readings that are within range, above the target, or below the target. As each reading is processed, the appropriate counter is updated, so the readings can be summarized clearly at the end. The code loops through each glucose reading while also tracking its day number. For each value, it checks whether the reading is below 80, and if so, classifies it as low. It then increases the low reading count, allowing the program to efficiently identify and count low glucose levels. The code checks whether a glucose reading is greater than 130. If so, it marks the reading as above target and increases the high reading count by 1, so the program can later summarize how many readings were high. This code classifies any glucose reading that is not low or high as within the target range. It labels the reading accordingly and increases the count of in-range readings, so the data can later show how many readings met the desired range. This line prints a clear daily summary for each glucose reading. It shows the day, the glucose level in milligrams per deciliter, and whether the reading is low, within target, or above target. The code counts the total glucose readings by checking how many items are in the readings list. This confirms the summary is based on the full set of reviewed data. The code prints a concise clinical summary of glucose readings. It reports the total number reviewed, then shows how many were within range, high, or low. It ends by confirming that the loop finished and that every reading was checked consistently. This script reviews daily fasting glucose readings and classifies each one as low, within target, or above target using set thresholds. It prints a brief daily result, keeps counts for each category, and then summarizes the total readings. The final overview helps identify patterns and highlights any glucose levels that may need attention. While loops. A while loop is useful when repeated data collection should continue until a condition changes, rather than for a fixed number of times. In clinical settings, this could mean recording temperatures until a patient is fever-free or checking glucose until levels stabilize. The loop runs while the condition remains true and stops when the stopping point is reached. When using a while loop for repeated measurements, plan what changes on each pass and what will make the loop stop. The loop may inspect, classify, count, or summarize readings, but it must always move forward, such as by going to the next reading or updating the condition. Clear starting conditions, repeated actions, and stopping points help prevent endless repetition. In health-related programming, while loops are useful for monitoring data until a condition changes. They can keep checking patient measurements, such as glucose or oxygen levels, until all readings are reviewed, a session ends, or a safety threshold signals the need for follow-up or urgent care. This makes them well-suited to real clinical situations where processing continues only as long as it remains appropriate. Python code, while loops. While loops are useful for repeated clinical monitoring because a condition controls whether monitoring continues. Each loop cycle should make progress toward an eventual stopping point. A list of glucose readings stores measurements collected during a monitoring session. These values can then be analyzed to see whether any glucose levels fall below a chosen threshold, which may indicate low glucose that needs attention. We start by setting the reading index to 0, which points to the first glucose reading in the list. This prepares the loop to check each reading in order from the beginning. Set the reviewed count to 0, so it can track how many glucose readings have been checked. Starting at 0 gives an accurate count when the monitoring loop begins. The loop first checks that the current position is still within the list of glucose readings, so it only handles existing values. It then gets the glucose reading at that position and uses it to decide whether the loop should continue or stop. The code stops the loop as soon as a glucose reading is at least 70. This ends monitoring once a safer level is found and avoids checking later readings unnecessarily. The code displays a brief message whenever a low glucose reading is processed. It uses the print function to show that the reading was reviewed, along with the current glucose value in milligrams per deciliter, giving quick feedback during each loop iteration. The code updates the count of reviewed glucose readings, then moves to the next reading in the list. This lets the loop continue checking readings in order until its stopping condition is reached. After the loop ends, we check whether the reading position is still inside the glucose readings list. If it is, the loop likely stopped because it found the first safe glucose value, which is then saved for later reporting or analysis. The program checks whether the loop stopped because it found a safer glucose reading. If it did, it reports that first safe value and indicates monitoring can stop. If not, it records that no safe value was found, so both possible outcomes are handled clearly. The code reports how many low glucose readings were checked before monitoring ended. This gives a quick, clinical summary of the low readings and helps evaluate the patient's status and the monitoring process. The script checks glucose readings one by one and reports any values below 70 milligrams per deciliter as low. It stops when it reaches the first reading of 70 or higher, then prints that safer value and the number of low readings reviewed. This models basic clinical monitoring, where low glucose is tracked until a safe threshold is reached. Logical clinical tests, combining clinical conditions. In clinical decision-making, combining patient observations gives more useful meaning than looking at one measurement alone. In Python, simple comparison rules can connect clinical thresholds, such as temperature, heart rate, blood pressure, and oxygen levels, to produce clearer messages. This turns repeated raw numbers into meaningful clinical descriptions that are easier to interpret. Combining clinical conditions means moving from simply recording measurements to interpreting how they relate. A program can look at repeated observations, such as daily readings or home logs, and identify when several signs together suggest concern. This helps produce clearer summaries by highlighting meaningful patterns and risk combinations instead of listing separate values. When combining clinical conditions, the result must be clear, accurate, and easy for students and clinicians to understand. Each condition should express a specific clinical idea, and combined statements should translate comparisons into meaningful language, such as linking temperature and oxygen status. Clear combinations support better programming habits, make rules easier to review, and reduce the risk of misleading summaries. Python code, combining clinical conditions. Combine clinical findings into concise, readable summaries by applying logical conditions with appropriate clinical thresholds. Keep the final printed output brief, clear, and focused on the key information. The example defines basic observations for patient A, including a temperature of 38.3 degrees Celsius and a heart rate of 112 beats per minute. These values provide simple clinical data for later evaluation. The patient's key measurements are an oxygen saturation of 94%, no confusion, and a fasting glucose level of 142 milligrams per deciliter. Together, these values summarize oxygen status, mental state, and blood sugar control. The patient's clinical state is assessed using 3 simple true or false checks: a fever if temperature is at least 38 degrees Celsius, a fast pulse if heart rate is over 100 beats per minute, and low oxygen if saturation is below 95%. These Boolean results provide a quick way to flag key vital sign concerns based on set thresholds. The checks combine simple clinical conditions to flag possible concerns. Fever with a fast pulse suggests a possible infection pattern, while either low oxygen or confusion raises respiratory concern. A fasting glucose level above 126 indicates high fasting glucose consistent with the diabetes threshold. The code starts by creating an empty summary list to hold brief descriptions of a patient's clinical conditions. This makes it easy to add condition summaries as patient data is processed, building a readable summary that can be updated or expanded as needed. The summary checks whether a patient has both fever and a fast pulse. If both are present, it records a fever with fast pulse pattern, which may suggest infection. If not, it records that the combined fever-pulse pattern is absent, making the clinical summary clearer. The assessment checks for respiratory or mental status concern by looking for low oxygen levels or confusion. If either is present, the summary notes a potential concern. If neither is present, it records that oxygen levels and alertness appear reassuring. The code compares a patient's fasting glucose level with the diabetes threshold. It then adds a summary message stating whether the value is above or below that threshold, helping categorize the result for the clinical summary. The output begins with the patient's name and a summary label, then presents each clinical summary item on its own line with a dash. This creates a clear, organized view of the patient's conditions that is easy to scan and understand. This script checks key patient indicators and produces a short clinical summary. It evaluates fever, elevated heart rate, low oxygen saturation, confusion, and fasting glucose above the diabetes threshold. It then combines these findings to report whether the patient has fever with a fast pulse, respiratory or mental status concerns, and high fasting glucose. Combining logical conditions. Logical operators let programs combine multiple conditions into one decision, similar to clinical reasoning. They express how related facts such as symptoms and patient history, work together to produce a true or false result. Clear decision rules help clinical summaries state whether observations call for follow-up, routine monitoring, or urgent review. Combining conditions means deciding whether several facts must all be true or whether any one of them is enough to act. In clinical summaries, this distinction matters because the logic must match the medical meaning. For example, a classification may require both a high glucose reading and fasting status, while an alert may depend on just one warning sign. Clear logical structure helps avoid confusing ideas like being stable unless any key value is abnormal, versus stable only when all key values are normal. Clinical summaries should combine conditions in ways that explain results clearly, not just label them as true or false. Plain language should state what the findings mean, such as when monitoring is needed or when a stable result is reassuring. Grouping related conditions in the right order makes the reasoning explicit, helping summaries stay trustworthy, explainable, and adaptable to guideline changes. Python code combining logical conditions. Combine logical tests in clinical summaries by using clear thresholds and symptoms to produce readable outputs. Keep examples small, predictable, and easy to follow so the main decision logic is clear. We store a patient's temperature readings in Celsius as repeated measurements over time. This data can then be used to check for elevated temperatures and help assess the patient's condition. The code stores two symptom reports as true or false values. The patient has chills but does not have breathlessness. These values can then be used later to help assess the patient's condition. Record the patient's oxygen saturation as 93, since this key vital sign helps assess respiratory status and whether urgent action may be needed. The process counts how many temperature readings are elevated. It checks each recorded temperature and increases the count whenever a reading is at least 38 degrees Celsius, which helps identify possible fever readings. This checks whether a patient has both a significant fever and chills. A significant fever is identified when there are at least two elevated temperature readings, and it is combined with the patient's report of chills. If both are present, the result signals a more concerning clinical condition that may need attention. An urgent flag is set when either of two warning signs is present: oxygen saturation below 92 or the patient reporting breathlessness. Using this "or" condition helps quickly identify patients who may need immediate attention. Follow-up is recommended when either of two warning signs is present: fever with chills or an urgent respiratory concern. If the patient has either condition, the follow-up decision is marked as needed. This combines symptoms and vital signs into a clear, concise medical recommendation. The code summarizes the patient's condition by reporting three clinical flags: how many temperature readings were elevated, whether fever with chills is present, and whether there is an urgent respiratory concern. The respiratory flag is based on low oxygen saturation or reported breathlessness. Together, these outputs provide a quick interpretation of the logical checks performed earlier. The code creates a clinical summary by checking whether follow-up is needed. If so, it recommends follow-up based on the combined findings. If not, it states that routine monitoring is reasonable for the day. This provides a clear, actionable message based on the patient's condition. The code prints a final clinical summary that explains whether follow-up care is recommended. This conclusion is based on earlier checks of the patient's symptoms and vital signs, giving clinicians a concise interpretation of the patient's current health status. This script reviews key patient signs to decide whether follow-up is needed. It counts temperature readings above 38 degrees Celsius, flags fever with chills when at least 2 are elevated and chills are reported, and separately flags urgent respiratory concern if oxygen saturation is below 92 or the patient feels breathless. It then reports these findings and recommends follow-up if any concern is present. Otherwise, it suggests routine monitoring. Not conditions. In clinical summaries, a not condition shows that a finding is absent or that a value does not meet a defined threshold. This is important because decisions often depend on what is not present, such as a patient not meeting fever or hypoglycemia criteria. Stating these results clearly makes the summary more explicit, readable, and easier for users to interpret. When using not conditions, be clear about which specific test is being reversed. A not result changes the interpretation of a threshold or alert, but it does not change the clinical facts. For example, not exceeding a concern threshold means that particular alert is not triggered, not that the patient is necessarily normal. Always tie not conditions to the exact criterion being tested to avoid making overly broad claims. Not conditions help clinical summaries clearly state when a patient does not meet specific risk or alert criteria. They are especially useful when combined with measurements, symptoms, and other logical checks, such as showing that readings do not match warning signs or fall outside alert ranges. Used well, they make it easier to see which condition was not met and reduce ambiguity in the summary. Python code, not conditions. In clinical summaries, clearly show when conditions are not present, and link any thresholds to the specific criteria they depend on. Keep the wording brief, readable, and focused on the essential clinical meaning. The patient's key health data is stored for later assessment, including body temperature, oxygen saturation, and whether a specific symptom is present. In this case, the symptom is marked as not observed. These values can then be compared with clinical thresholds to help evaluate the patient's condition. We define clinical thresholds to flag possible patient concerns. A fever is identified when temperature is above 38 degrees Celsius, and low oxygen is flagged when saturation falls below 92%. An urgent alert also requires urgent symptoms to be present, so patient data can be checked against clear clinical criteria. The code first turns each urgent care check into a simple true or false result. It checks whether the patient has a fever, whether oxygen saturation is too low, and whether required urgent symptoms are present. These basic Boolean results can then be combined later to form more complex medical decision rules. An urgent alert is triggered when the patient meets both the fever requirement and the symptom requirement. The alert condition is then expanded so that low oxygen saturation can also trigger it on its own. In short, the system raises an urgent alert if the patient has fever with the required symptom, or if oxygen levels fall below the cutoff. The code presents a concise clinical summary by first printing a header, then showing the patient's temperature in Celsius and oxygen saturation as a percentage. Together, these outputs clearly display key vital signs in a readable format for quick assessment. The check uses the not operator to identify when a patient's temperature is below the fever threshold. If the fever criterion is not met, the program prints a message stating that no fever threshold has been reached. This makes the clinical summary clearer by showing which condition was not satisfied. The code uses a logical not to check whether the patient does not meet the low oxygen criterion. If the oxygen level is not below the cutoff, it reports that the criterion is not met, indicating the patient's oxygen saturation is within the defined safe range. The code determines whether an urgent health alert should be raised using predefined rules. It checks the alert status and prints one message if no urgent alert is needed, or another if the rules do trigger an urgent alert. This gives a clear indication of whether the current criteria point to an urgent condition. This script checks a patient's temperature, oxygen saturation, and symptom status against set thresholds to decide whether an urgent alert is needed. It reports the measurements, uses logical negation to show when fever or low oxygen criteria are not met, and then gives the final alert result. In this case, the temperature is not high enough for fever, oxygen saturation is not low, and the symptom is absent, so no urgent alert is triggered. In this lecture, you learn to write conditional statements that classify medical values using clinically defined thresholds. Use loops to process repeated measurements such as daily temperatures or glucose readings. And combine comparisons, logical operators, and simple output to create readable clinical summaries. In the next module, Module 2, we will go over medical data structures. Thank you for your attention. See you all in the next lecture.